is Cauchy integral formula. Most of the time, whenever I will write it as CIF, just an acronym, not a standard notation. Let F be an analytic function within and on a simple closed contour C. Then for any Z naught in the interior of contour C, we have the value of the function at Z naught is given by the integral of fz upon z minus z naught. नोट करना है इसको अच्छे से ध्यान से देखना ये फॉर्मूला about C. This is the Cauchy's integral formula. Note here, you have a contour C, and then what you are going to do, what you are having, that this function is analytic. This function is analytic. This event had changed many things, so I need to find now colors somewhere else. What is the color? Colors यहाँ पर ऊपर कर दिए उन्होंने. Okay. So this is the contour C, and the hypothesis is that this function is analytic on this contour C, and it is analytic on contour and inside contour. It's analytic at points of the contour also, and it is analytic inside the contour also. Then what happens? Then the interior part, if you choose any point in the interior part, then it says that the value of the function inside this contour is completely determined by the values of the function on the contour. क्योंकि आपके पास इंटीग्रल में कौन सी वैल्यू यूज हो रही है? You are taking the integration of contour C, and then f of z, the value, then inside the integrand is being taken over this contour C. So the Cauchy integral formula is what it says that the value inside this contour, it is a domain also. If you take domain D, and if you take C to be a simple closed contour, then it says that the value inside this this contour is completely determined by the value of the function on the contour. So this is a very powerful result that if you want to determine a value of the function, if you have you know that what is a function, and if you know what are the values of the function on this contour here, then with this knowledge you can find all value of the function at all the points inside this contour, and this is given by this formula. And this formula will be, this is a very powerful formula in complex analysis. It will be used at many places. You might see it will have far-reaching consequences on the on establishing several important properties of analytic functions. But let us do its proof first. Let's prove it. That what is its proof. So the proof is, let me draw a diagram again here, a figure here. You have a contour C, then what you have a point inside here and Z naught, and you want to establish that the value of this function at this Z naught is equal to something when integral over some function. What is that function? But that function takes the values on the contour C. So what we can do, note that since this interior part of a contour is always a domain, and since interior part of C, this is not the topological interior. This is the interior means the inside region of this is a domain. It is always a domain because it is a simple closed contour, and so it is connected. If it is not simple closed, then still it is it's a open set. It's a domain. So for any point inside here, I can find a neighborhood of this point. I can find a neighborhood of this point of certain radius r naught, such that let me write there is some r naught greater than 0, such that the closed disk centered at r is contained inside this interior region of C. This is always possible to do because this is an open, by definition of an open set. By definition of open set, it is the open disk, but if you take the half the radius of that open disk, you get the closed disk as well. So this is always possible. Now, this function fz upon z minus z naught is analytic. Is analytic everywhere. When I say that everywhere means the region that is under consideration. Everywhere on let me write this R to be contour C union its interior part, and R is equal to region everywhere except possibly at Z naught. This may not be analytic at Z naught. When I say that may not be, because it may be analytic at Z naught, but you just assume first that it's not analytic at Z naught, because at Z naught denominator part goes to 0. So it is not an analytic at Z naught. Now that means mm, on this part of the region, on this part, this change all the settings. I have to find out. So on this part, the function in particular, except at Z naught, this is analytic, but at least on this part it is analytic. Now this shaded region is nothing but it's a multiply connected domain. It's not simply connected, it's a multiply connected domain. If it is a multiply connected domain, I can use the Cauchy's theorem. And for multiply connected domains, you have two curves. One is this circle. Let this circle be denoted by C naught. I'm denoting it by C naught. Let C naught be the circle. This is the circle Z minus Z naught equals to R naught. So then by Cauchy-Dorset theorem that we discussed in the previous lecture, for multiply connected or annular regions, you may also call it multiply connected domains. What do we have then? We have that integral of this function fz upon z minus z naught over the contour C is same as the integral of the function over this circle C naught, and both taken in positive direction. When both are taken in positive direction, we will have that integral over C of fz minus z naught dz is equal to integral over C naught fz upon z minus z naught is equal to dz. Let me call this some. So now what is left to be proved is this integral need to be looked into closely. This one, I need this integral, अगर मैं इस integral को show करूँ कि I have to show actually this integral to be value of f at z naught equal to 2 pi I. If I am able to show these things, then the result will follow, because we need to show that f of z naught equal to 1,125 and shift to the other side. So now let us do computation and let's work on this integral taken over this circle, because the function is not analytic only at z naught. If it is not analytic, and so then we have this option here that we can make this disk smaller, as well as smaller, as much smaller as we needed. But also note that these concentric circles that you see with the yellow shade and the pink shade, the value of this integral over all these circles is same, because of again the Cauchy theorem. And then we have to show that the value of this integral is same over all these integrals. So that means we can choose an appropriate value of the radius for which we are able to compute the value of this integral. But how we are going to compute this? Let me write. Now, I can write this integral f z upon z minus z naught dz over this circle. Just to signify this circle, I'm writing z minus z naught equals to r naught instead of c naught. Then I can write it as f z naught integral over, let me write again c because the notation is becoming large, c naught. I can write it as dz upon z minus z naught plus, I'm writing again c naught and I'm writing it fz minus fz naught. So what I did, I just added fz naught and subtracted fz naught from fz, and then I got this expression z naught dz. Okay. So, but what is the value of this integral? You have the circle. If you substitute, if you give it. If note that on this is a c naught is a circle, on this circle z minus z naught equals to r naught, you have z minus z naught equals to r e I theta, so that d of z is equal to I times r e I theta d theta, and this implies that you will have this dz upon z minus z naught equals to I r e I theta d theta upon r e I theta, and all this thing, all these r e I theta and r e I theta will cancel out. You will be having I d theta, and this implies that then this integral, which is our c naught dz upon z minus z naught, with the polar representation, the limit of the theta ranges from 0 to 2 pi over the circle. It is I d theta, and the value that is left to you is 2 pi I. So the value of this integral is 2 pi I. So that means I can write this integral to be equals to 2 pi I f at z naught. But we have an additional integral also there, which we do not require if we want to establish the Cauchy integral formula. And what is to be done for this is to show that the value of this second integral here on the right hand side is 0. So let us try to deal with this now. Let me call this as a second equation. This is it. Now f is analytic. F is analytic, so f is continuous. F is continuous at z naught. When I so for any arbitrary small number epsilon bigger than 0, by continuity of the function, I can always find a delta bigger than 0, such that this inequality holds that value of fz minus fz naught, this distance is less than epsilon, whenever z minus z naught is less than delta. So what we want, but here you have z minus z naught over the circle c naught, and the radius of the circle c naught is radius r. Then what we can make this circle, as I said here, I can make r naught to be less than delta. This is my choice. This is we can always adjust things. We can make r to be arbitrarily small. Still, the disk will remain inside here. So then choose if necessary. If r is already less than delta, then you don't need to choose. But if the need arises, if needed, choose r naught to be less than delta. Then you can apply this definition of the continuity of this function over the circle C. So then you have this modulus over C naught fz minus fz naught upon z minus z naught dz. First, you use the property of the line integral that when modulus interchanges with the integral, the inequality is less than C naught mod of fz minus fz naught upon mod of z minus z naught into mod of dz. And say according to our computation in the previous slide, mod of fz minus z naught has to be less than epsilon, and c naught is a circle, and on circle z minus z naught is equal to mod of z minus z naught is equal to the radius. It has to be radius r naught times integral. Let me write now, instead of z, I write z mod of z minus z naught equals to r naught into mod of dz. We have this. Now, what is this thing that I have enclosed here? Can anyone tell me what is it? What is this thing? Bolo?
1 by r.
Yeah, it is the arc length of the circle. So this is arc length. So this has to be epsilon upon r naught into 2 pi r naught. So r naught and r naught get cancelled. So what you get the value of this integral over c naught f z minus f z naught upon z minus z naught dz is less than 2 pi epsilon. And remember, epsilon is an arbitrary number. We can make it as small as possible. And the integral in this, what you say, integral within this modulus is a constant quantity. So if it is a constant quantity and we have this option here to make this integral arbitrarily small, that means this must go to 0 as epsilon goes to 0. We have this liberty. If it goes to 0, that means our appropriate circle, we will have the value of this integral fz minus fz naught to be, this has to be equal to 0. This has to be equal to 0. So this happens to be 0. That means from this equation here now, you have value of this integral 0. What is left to you now is, let me write from equation second. Now you have integral over the original contour c f z upon z minus z naught dz is equal to the first value that you obtained was 2 pi I f h z naught plus the another integral, the value is 0. This implies that value of f h z naught is equal to 1 over 2 pi I integral c f z upon z minus z naught dz. This is the Cauchy integral formula. So बोलिए कोई दिक्कत? You have any query? नहीं है? चलिए then. Let me illustrate the use of that. It has so many uses, but at least you can now integrate any kind of function which has finite number of singularities inside the given contour. Finite number of singularities means where the function is not defined, Uh, let us integrate this integral. Let me consider an example. Let me integrate this integral over c. It is z dz upon 9 minus z square into z plus I. So the first thing is you need to identify what is the contour. Where contour is given is a circle of radius 2 around with center 0. So you need to find a kind of Cauchy integral formula. You have to apply Cauchy integral formula, but for Cauchy integral formula, you have to identify what should be the z naught and what should be the function f z, and that will depend upon if you first draw what is this contour C. You have this contour C. It is a circle of radius 2 at center with center 0. So you have here, you have 1, you have -1, you will have -2, you will have 2 something I minus I. So here, if you put fz is equal to z upon 9 minus z square, look at this function. This function is analytic on this circle and within circle also, because it doesn't. The only problematic points where you might have doubt over the analyticity of this function is the points where the denominator is 0. Where is the denominator 0? Denominator is 0. The 9 is equal to z square. That means at z equals to plus minus 3, you have the problem. But look at this z equals to plus minus 3, they do not lie inside this circle. You have minus 3 here and you have plus 3 here. They lie outside this circle and do not lie inside. Therefore, the function f is then fz is analytic. This is analytic inside the circle. And not only inside the circle and on circle as well. On circle, the given circle mod z equals to as well. It is analytic there because at this point is also every point on this circle function is analytic. It doesn't, the denominator has no zeros on this. So this is an analytic function. So we can take this. The other thing is that why I have brought z plus I. If you take z plus I in the denominator, you will have a problem there, because I is inside this integral, is in this contour, and at I you may not, the function wouldn't have been analytic there. So we dropped it, but it will work with us. It will here minus I will work as a z naught for us. Then by Cauchy integral formula, Cauchy integral formula, I can write this value of f at minus I. See, by Cauchy integral formula, it would have been 1 upon 2 pi I integral over this circle mod z equals to 2. It should have been f of z upon z minus I to z minus I to z plus I हो जाए. तो आप इसको सब्स्टिट्यूट करो यहाँ वैल्यूज, तो आपके पास आ जाएगा 2 पाई आई को मैं राइट हैंड साइड शिफ्ट कर लेता हूँ, तो 2 पाई आई आपने लेफ्ट हैंड साइड शिफ्ट किया, f minus I shift here, it is equal to, now I need to find eraser also. Okay, here it is. Okay. Okay. So what is it? What is it? You just substitute the value of, let me change the color so that it becomes differentiable to identify. And it is mod z equal to 2, and then it is, what is fz? Fz is z upon, will be z upon 9 minus z square, and you are multiplying it with z plus I also into dz. But this is the integral that we want to evaluate. This is the integral that has been asked to be evaluated. So the value of this integral comes out to be 2 pi I times f minus I. And now you substitute minus I here, what you get? What is the value of minus I? Now 2 pi I f of minus I is equal to 2 pi I minus I. It has to be z upon 9 minus z square है ना, minus I upon 9 minus I square. Just compute this value. It is 2 pi I. It has to be I और I क्या होगा, नोमिनेटर में I और I का मल्टीप्लाई करोगे तो -1 और पाएंगे, ऑलरेडी आपके पास माइनस कैंसिल हो जाएगा, इनटू 1 upon, if you look at this is 9, what is square, it will be minus, तो माइनस कैंसिल हो जाएगा, बट आई स्क्वायर का आपके पास -1 होगा तो माइनस माइनस प्लस हो जाएगा, it is 2 pi upon 10, and is actually 12 pi upon 5. Hence the value of this integral, that was our circle of radius 2, z dz upon 9 minus z square into z plus I is pi upon 5. See how easy it is now to compute this integral. This is another method. You can compute it by using your classical method. You just take the parameterization of this circle curve. But Cauchy integral formula, you do not require this parameterization of the. You just need to know what is this thing, and you just have to identify what should be the function. Then there is a one-step process, almost a one-step process to compute the value of the integral. So, anything left to be explained in this step? बोलिए. Is it clear to all of you?
Yes, sir.
Yes, sir.
So you might have some exercises. You have books, and you just go through the book of Churchill, and you have Gamlin also. It is same everywhere. You just try to solve more and more examples, more and more integrals by using Cauchy integral formula. We are going to tomorrow. We will be doing a more general version of this Cauchy integral formula for derivative of an analytic function. That is a much important and much stronger result than this. But today we will stop with this. If you still have any question, I'm